So welcome again. So in this session, we are going to set and apply the second shift theorem for Fourier transform. So the theorem states that if f of k is the Fourier transform of the function f of t, then the Fourier transform of f of t minus alpha is the same as e raised to power negative I alpha k times f of k. So that's the statement. Then let's now do an example to illustrate this. But then we can simply prove this. So proof. So the Fourier transform of the function f of t minus alpha is the same as the integral from minus infinity to positive infinity of f of t minus alpha e raised to power negative ikt dt. This by definition. Now, we know that the Fourier transform of f of t is given by integral from negative infinity to positive infinity of f of t e raised to power negative I k t dt. So this is what you are calling the f of k. So then it means that if I write, if I let k t, okay, so this just by definition. So if I let my k t minus alpha to be a function u or a variable u, then this implies that dt is the same as du, and then t itself the same as u plus alpha. So that now from this definition, we'll have the Fourier transform of f of u will be the same as, now when, remember these are limits for t. So when t is infinity, then u is also infinity. And then when t is negative infinity also, u is negative infinity. So limits are not changing. So we'll have negative infinity to positive infinity of f of u e raised power negative I k, but where there's t, we replace by u plus alpha, and then t. So that's the value of t, and then dt the same as just du. So then we'll have the Fourier transform of f of u is the same as integral from minus infinity to positive infinity of f of u, and then this can be written as e raised to power negative I k u, and then times e raised to power negative I k alpha, and then du. So which means that because the variable here is now u, these are constant, we can factor it out. So we'll say the same as e raised power negative I alpha k or k alpha integral from minus infinity positive infinity of f of u, and then e raised power negative I ku du. So you see clearly that this is the same as e raised power negative I alpha k, and then this part is just the definition of the Fourier transform of the function u. So just f of k. Because you see, from definition, if you write negative infinity to positive infinity, f of t e raised power negative I k t dt. This is what you say that this is the Fourier transform of f of t, which we denoted just by capital F of k. So the same thing here, that this is the same structure. The only difference is that now it be for the function depending on the variable u, but then its notation is just capital F of k. So the proof ends there. Now let's quickly do an example to illustrate. Illustrate the application of this second shift theorem. So given that example, given that when f of t is given by 1 for absolute value of t less than or equals to 1, 0 for absolute value of t outside that interval, and then capital F of k is given by 2 sine of k divided by k. Apply the second shift theorem. To find the Fourier transform of the function g of t given by 1 for t between 1 and 3, 0 otherwise. And then once we have done that, verify the result directly. So let's see how to work out this. So note that the function g of t can be drawn on a graph, and we'll take this form, this t-axis, this is the g of t. So 0. So you have 1, 2, 3, and then so this is 1. So I'll have here so this is the what you are calling the g of t that has 1 when 1 is between when t is between 1 and 3, and 0 others. So we see that clearly g of t is a function f of t translated two units to the right, i.e. g of t is simply given by f of t minus 2. Now we have been told that f of k in this case is given by 2 sine of k divided by k with the Fourier transform of the function f of t. So then by the second shift theorem, I will have the Fourier transform of g of t will be given by the Fourier transform of f of t minus 2, which is the same as e raised power minus 2 I k times f of k, and this will give us 2 e raised power minus 2 I k sine of k, and then you divide by k. So this is what that value or the transform gives. But then now, if you were to do without the second shift theorem, then the answer will be, so verification, we just start from definition that the Fourier transform of a function g of t will be given by the integral from minus infinity to positive infinity g of t e raised power negative I kt dt. But because the function is only defined from 1 to 3, this interval reduces to 1 to 3, And then from 1 to 3, the value of the function g of t is 1. So we just have e raised power negative ikt dt. By substitution method, we'll have negative 1 over ik, and then e raised power negative ik t from 1 to 3. So putting in the values of the limits, we'll get negative 1 over ik into e raised power negative 3 ik minus e raised power negative I k. And you see we can write this one as e raised power negative 2 ik into, so just say ik, it's a negative sign here. So when I factor out this, I need to multiply this one by e raised power negative ik, and then e raised power negative ik. But this now should be plus, so that now I still have the original expression. Remember, this is the Fourier transform of g of t. This is the Fourier transform of g of t. This is the Fourier transform of g of t. So then I can remove this negative sign, and then I'll have e raised power ik minus e raised power minus ik, and then divided by ik, and then everything here is multiplied by 2 e raised power negative 2 ik. But we know that e raised power ik from Euler's identity minus e raised power negative ik is simply 2I sine of k. So then this step leads us to Fourier transform of g of t the same as e raised power minus 2 ik over ik, I multiply by 2I sine k. And you see I and I cancels out. I cancels out, so that this will have 2 e raised power negative 2 ik sine of k divided by k. And indeed, is the same answer that you obtained by the second shift theorem. 2 e raised power negative 2 ik sine of k over k. So that's how we apply the second shift theorem. Thank you.